Well, let me have your attention. Please be seated. We'll get the afternoon program underway. The first panel this afternoon is a panel that is dealing with the human effects of long-duration spaceflight. The discussion will focus on environmental events in flight, evidence-based. And we're very privileged and honored to have Dr. Valery Bogomolov as the moderator of the panel. He is also deputy to Dr. Anatoly Grigoriev, and who is of course, Dr. Grigoriev is the general director of the IBMP, and Dr. Bogomolov is his deputy. He has served as the co-chair for the Phase 1 Medical Operations Working Group, who have been responsible for defining healthcare systems requirements in support of astronauts and cosmonauts involved in cooperative missions. So, Dr. Bogomolov, your panel.
Dear colleagues, please allow me to introduce the panel members. To my right, we have Marcelo Vasquez, Dr. Nigel Packham, Mary Van Balen, Dr. Novikova, and Mr. Petrov. These are the specialists who are unique in their own right. These specialists are unique in their areas of specialization. We have very important topics to discuss: radiation safety, as well as the quality of air, environmental control systems, and biological monitoring. During my introductory remarks, I would like to say that the environment on the ISS is of paramount importance. It's an extremely important medical factor because it's a closed loop, the ISS is, and therefore we need to monitor, sustain the appropriate levels of environmental control. If we have any deviations from the acceptable standards, are usually the cause of medical consequences and medical and technological problems that we face on the ISS. Let me list them. Physical consequences, humidity, temperature, acoustic levels, as well as the lighting conditions, air quality, which is necessary to support the physiological needs of humans on board the ISS. In addition to that, the long-duration flights and the manned operations means that we have human beings as well as other living beings, such as microorganisms and bacteria, that give an example of another ecological group. And their health can impact not only their physiological state, but technical systems. Therefore, I would like to ask the panel members. Marcelo, please, you'll be the first to take the floor. And if you like to briefly touch upon the issues that you work on, radiation safety in particular.
Thank you very much. I think the radiation issues have a consensus. This is one of the major concerns for spaceflight, in particular for long-term spaceflight, and also what kind of spaceflight in terms of low Earth orbit or beyond that. As particular concern, as everybody is aware, that go beyond the protection of the magnetic field will pose an incremental risk due to radiation exposure for protons from the sun, and galactic cosmic rays. Welcome to David Wolf. And I think it's a concern for these missions, and it's a challenge. It's a really challenge. And NASA have a really important program addressing those issues, the Space Radiation Health Program element, addressing basic mechanisms and late effects and acute effects. And NSBRI also have radiation research efforts. In particular, we are interested from now on acute effects oriented to support risk mitigation and countermeasure strategies for lunar operations, in particular for solar particle events. With this new realignment in terms of operation needs, one of the main concerns now for the vision of exploration is deal with solar particle events during mission to the moon, in particular during EVAs. And in particular, acute effects, mainly prodromal syndrome, skin reaction, hematological changes, potentially induced by the doses of radiation that is expected in the worst-case scenario, based on calculations made by NASA. We don't expect lethal events based on the worst-case scenario during the EVA operation, but there is a potential risk for acute effects, prodromal syndrome during EVA and the course of one of the program on mission to the moon. In terms of Mars, it's a completely different, as you know, a different problem, because we need to deal with galactic cosmic rays. And one of the problems in terms of radiobiology, the galactic cosmic ray, is we don't know all the biological mechanisms that will explain the potential risk for this. There's a lot of uncertainties with that. So it requires a very basic program to understand what are the basic mechanisms of radiation damage in order to develop countermeasures. The good news in terms of lunar operations is that protons, and there's some consensus, they are kind of similar in terms of conventional radiation, gamma rays, X-rays, and we have some data for many years in radiobiology, radiation therapy, nuclear emergencies, and we have some idea of the mechanism of action. So we are in a little more better position to develop some medical countermeasures that will support lunar operations. But NASA and NSBRI, through the roadmap, bioastronautic roadmap, identified some of the important risks for lunar and Mars operations. And just to give you a brief list, and one of the big concerns, cancer induction by radiation, central nervous system late and early damage, acute effects, and tissue degeneration. And these are the main risks. And also, those risks will change in terms of priorities if you're talking about lunar missions and Mars missions. For lunar missions, I think it's a consensus. The acute effects is the main concern, and late effects for Mars mission for sure. And develop countermeasures is very difficult for galactic cosmic rays because we don't know the mechanisms, but I think we are in a good path to come up with well-developed also from the radiation therapy and treatment of patients with radiation signal on Earth. We can come up with some candidates that can be tested for lunar operations, plus other operational and shielding configuration for moon operations. So we are working very intensively in these areas, and we are working with NASA and try to develop those strategies for 2020 for lunar operations.
Спасибо. Я прошу.
Thank you very much. I apologize. I failed to introduce one of the most important panel members, David Wolf. I kind of lost him. I couldn't find him to drag him to the panel. So now we repair the situation, and let me introduce him to you. Well, since we're talking about radiation, I would like Mary Van Balen to take the floor, because you are the leading specialist on radiation, it is my understanding, and therefore maybe you'll share your insight on radiation
Well,
issues.
thank you for those kind words. I'm not sure I'm a leading specialist. Marcelo talked about a lot of the research that needs to be accomplished, or a lot of the work that is ongoing for answering many of the questions involving the effects of radiation exposures in space. Peggy Whitson also talked about how conservative it was felt that the limits that and the policies that NASA have adopted. And so I guess I'd like to talk a little bit about the challenges I see operationally working within that environment. Currently, we're planning missions that with what we know today. And so we are looking at lunar missions within NASA with the knowledge that we have today. We are writing requirements for vehicles with the knowledge that we have today. We're developing hardware with the knowledge that we have today. And I think one of the important challenges will be that we'll have to remain flexible and change those requirements within the programs as we learn more. And the more we learn, the less conservative potentially that we can be within our future operations. So I'll be brief with my remarks.
Спасибо.
Thank you. And I would propose Vladislav Petrov to take the floor and continue this part of our discussion. Thank you, Valery. I would like to elaborate not on technical aspects, but closer to our medical aspects. What is radiation? How does it impact a human body? And what areas require specific focus? In order to understand the peculiarities of the impact of radiation on a human, let me explain what is the space radiation. Unlike the radiation on the ground, when we deal mainly with electrical and magnetic rays and neutrons, in space the main components is charged particles. Unlike gamma rays, they create very dense ionization inside the body, and it can lead to evaporation of cells on its path. And there is another factor which is specific just to space environment. You might have heard about it. We heard about the solar particle events or solar proton events. These are powerful explosions on the sun that charge out the particles and that create the elevated radiation level. And on Mars, or on the way to Mars, we'll have similar events, but worse. This is similar to the Chernobyl explosion we had, but it's not a contingency like it was in Chernobyl, but it will be a nominal everyday existence. And this is very important to take this into account. The third factor or challenge, since this charged particle create radiation inside the body, the dosage inside the body of the same human will be different depending on the source of the radiation. Therefore, it is really important to calculate not an average radiation, but to look into the exposure of a particular organ inside the body. And the last factor, if we have a very good protection, geomagnetical protection, being close to the ground, to Earth, flying further away from the Earth, the dosage of the radiation will be on a different magnitude. And this is a hazardous phenomenon that we have to deal with. This is one statement. Then, second statement, there are no good dosages. Every radiation dosage is a harmful one, and therefore we need to take this into account. Third factor, when flying to Mars and to the Moon, it is important to take into account not only radiation and biological consequences of radiation rays, but also the ergonomical factors, how the functionality of the human body will be impeded, and what lethal factors will play their role. Therefore, these risks have to take into account when we design future programs. When we fly to Mars, we'll have to take everything from the ground. Therefore, every gram of up mass will be costly. Not knowing the exact consequences of radiation, not knowing the properties of radiation and how the dosage is distributed inside the body can lead to unreasonable and illogical amount of cargo items that we would want to take with us, since we don't know what we're dealing with. And allow me to enlist a number of projects that we have in Russia today that would enable us to shed some light. You have heard about the Matryoshka experiment. Bill Gerstenmaier mentioned that this is the payload activity that will learn how the radiation is distributed inside the body and what levels of exposure we have. Then the next program is the biological effectivity of radiation. We need to know how radiation affects a human body, starting from a cell to genome, etc. We have to have molecular studies, and they have to be large-scale studies. And we plan to have this experiment with the participation of monkeys and how the tissues will be affected, starting from a cell to plasma. We plan to expose the subjects to radiation for about 560 days, which will be similar to Martian conditions, which will be chronic exposure with some acute reaction. And another question, ethical question. We have individual resistance and the cytogenetic research and how it impacts the body. And we hope to get the results from the research that we're conducting today. Also combine the worst-case scenarios. The BION project that Valery mentioned before is designed to have these studies in 2013. Then the radiation hazards. On the ground, we can say that this is the threshold, this is the hazardous level. If we can say that this is safe and this is not safe. In space, there is no levels that are safe, because any exposure in space would lead to hazardous levels that the person undergoes on the ground. So let's say if it's 25 bar, and the possibility of exceeding this level is guaranteed. The second level of exposure will be multiplied by 10 or even more. Therefore, there should be a special approach developed which will take into account all the consequences of radiation in space, of exposure, and the limits, which will be not for the whole flight, but for every particular radiation event or radiation environment. Therefore, we have to have highly specialized calculations. Of course, I can elaborate for a long time on different exciting projects that we're working on, but hopefully I was able to enumerate the most important projects. Thank you.
Но одной радиационной безопасностью проблемы обитаемости не закрывается, поэтому я просил бы высказаться вас, господин.
Thank you. First of all, I have to say, it's great to be here. There's some colleagues and friends, and my whole mentorship of my history is pretty much here. It's fabulous to see you. And we're engaged in an amazing voyage here. There are open questions in radiation, and we don't know how bad it's going to be, and we know it's going to be hard to treat. And one thing comes to my mind I'd like to mention. We may need to reconstitute the complete hematopoietic system en route several times, myeloid, erythroid, lymphoid. The technology exists to do that now with stem cell reconstitution. I think we should be considering that. We may lose the hematopoietic system. We may want to knock it out and restart it, and we can easily store that. I think that's the only thing new I have to say over what's been mentioned on radiation.
Хорошо, спасибо.
Thank you, Dave.
Я бы предложил
I would propose
Пакхаму
to give the floor to Nigel Packham. And Nigel, if you could talk about the issues that we deal today and what you envision we'll have to face in the future.
Oh, thank you, Dr. Bogomolov. I'm actually surrounded by radiation workers here. I'm not sure if it's very safe. I can't let Gerst's comment about the volatile organic analyzer go unpunished. Just a comment on that, it's not just the availability of hardware and a well-trained crew, it's the combination of the two. Just one example there is that Bill MacArthur spent a period of 2 days with a 54-page procedure taking out 78 non-captive 3mm fasteners and didn't lose a single one. So the crew is our asset, their eyes and ears on orbit, so it speaks volumes of why we do human spaceflight. We've talked a little bit about radiation exposure and the unique environment that our crew members are exposed to on orbit. They're exposed to another unique environment, which is the fact that they are exposed to the environment 24 hours a day. So the use of ground-based standards, such as OSHA standards, time-weighted average, really doesn't hold weight when you try and transition from a normal working environment to a 24-hour exposure. There is nowhere else to go to get away from the atmosphere for a crew member. So anything that happens to the atmosphere is going to expose the crew. The other important thing to note, I think, is that on ISS to date, and I think I can say for the future, at least surface-based life support systems, they are going to be closed systems where recycling is at least a component of the life support system. So if something happens to the air, for example, it's more than likely going to end up in the water system. And we've seen this time and time again on ISS and on previous flights. So it's a multifaceted hit when you have an event happen. Let me talk about two things in terms of the atmosphere. The two components are the major gases such as oxygen and carbon dioxide. I'm really not going to touch on those that much, although there is anecdotal evidence that the partial pressure of CO2 has had an effect on ISS crew members. Whether or not that is something that the crew reports based on knowledge of the concentration, or whether it's actually real or not, is yet to be determined. But they seem to perform better, at least psychosomatically perhaps, when the ppCO2 is below about 2 or 3 millimeters of mercury. The other area I'd like to touch on is in the area of trace contaminants, which in fact the volatile organic analyzer was designed to detect. However well you design a spacecraft and the systems that support it, things will happen. And they're things that you will not expect to happen. And in fact, if you look back through the history of space station, shuttle Mir shuttle, and the shuttle program, there has been at least one event per year that has occurred. The predominant type of event has been a pyrolysis event, not necessarily a fire, although the Mir fire was the worst obvious case in that respect. Also in the history of those three programs, the likelihood is you're going to have at least one catastrophic event in the life of the program. I don't mean that somebody is going to be, we're going to lose a crew member, but it may have the potential for loss of crew or the loss of the mission. So my belief is that however well you design the spacecraft, you also have to be prepared for contingency events to happen. As far as I know today, the Constellation program has decided, at least as of today, that there is no need to monitor for trace contaminants. I think that's a mistake, personally. The approach that they are taking is that as long as my life support systems are working the way they're supposed to work through telemetry, that you don't need to bother to monitor for trace contaminants. In my view, that's exactly the wrong way to go about it. Perhaps not for CEV going back to station or to the moon, but certainly for a lunar base, I think the potential for something happening there where you are now days away from home rather than hours when you can just jump in a Soyuz and come home. I think the risk we inherit from that type of decision is too much of a risk. So I have concerns about the future. I think, in general, ISS environment conditions are extremely good. We've had our upsets, but in general, I think we've kept a good handle on what we've seen so far. And that's about it.
Спасибо. Я хотел бы
Thank you.
к этому добавить, что
And I would like to elaborate
качество
that the
воздушной
quality
среды,
of
оно
air
слагается
in
из
environment
многих компонентов. Это
is a
и
multifaceted problem, and it comes from different factors: anthropometric,
газовыделение,
the gas
тех материалов,
quality, and the materials, the design materials that are used for the design of the vehicle, as well as the cargo items that are delivered. Today, if you look at the total exposure of pollution, has a tendency to be elevated. Therefore, we have to prepare the modules that will be docked to the ISS with more margins of safety, as well as we have to have very effective methods for monitoring of the environment and to have good, reliable systems for cleaning and purification. And these risks that lead to some issues that we have. On the other hand, any failure of environmental control system, be it oxygen generation or CO2 removal system, can potentially be hazardous because of some serious medical consequences, which might require some intervention. In addition to quality of air, we know that another big issue for us on the ISS, on the Russian stations, the Soyuz and Mir, was the noise level, the acoustic pollution. Therefore, to normalize, to regulate the levels, to come up with good sound requirements for noise level is very important. And any measures to diminish the noise level are of paramount importance. The closest to professional disease factors for astronauts and cosmonauts is the damage to hearing after the long-duration flight. In some cases, it brings to the damage of the ear nerve and the diminishing ability to hear. I also mentioned before that another serious factor for us is ecological and microbiological on the ISS. Microbiological safety is of extreme importance today. Therefore, I would ask Professor Novikova to express her opinion on that subject. Thank you. Manned space flights have the main ecological partner is a microorganism. Currently, on orbital stations, we discovered about 300 of different types of bacteria and microbiological organisms. The microorganisms have a very unique capability. They can populate the environment using different design and construction materials as an environmental niche. After the genetical research that we have performed on board the Mir space station, we confirmed that we found the ancestors of those microorganisms after 7 years after first discovering those stems. We were saying, and it's a joke, of course, that the true owners and residents of the station are not the crew members, but the microorganisms. And we have significant medical technical and technological risks related to microorganisms. I'm not going to cover the medical risks because we are all fully aware about medical risks related to microorganisms, but the technological risks I'll probably mention because sometimes the microorganisms populate polymers and metals, and sometimes they damage and bring a biocorrosion. We had a number of examples that in the past some of the hardware items would fail and some of the environmental control systems would fail, such as the water regeneration system from the condensate, just because we had an extreme growth of organisms on the surfaces. Therefore, for future flights, for exploration flights in the future, this problem becomes of paramount importance. And I would like to say the following, that among those microorganisms that we discover, we find sometimes not only the human flora byproducts, but in addition to those, the microflora is represented by other resources such as water, air, etc., that get to the station or the module during the processing or when we prepare the cargo items for the traffic flow.
And the methods that we use today that prevent us from facing this problem with microorganisms are mostly having to do with biocides. That is, of course, on the one hand, convenient. However, biocides have dramatic drawbacks. The first drawback is that their effect is time-limited. These procedures have to be repeated. They're also difficult and labor-intensive for the crew members. Another aspect is that it is impossible using the biocide to resolve this problem in the areas that are hard to access. So in the future, particularly for interplanetary flights, it would be very important to develop new technologies such as making sure that the material themselves have antimicrobial properties. We're working on those technologies, and basically it is a surface modification of polymers and putting antimicrobial films on the metals, on the surface of the metals. As an example, I would like to point out that we're going to send a new module to the ISS, and it's called MLM. So the panels, the interior panels of this module will be manufactured with the application of this technology. And another thing that's very important for spaceflight is to prevent microorganisms from entering the environment, and we need to employ all sorts of different methods for that. Pulse ultraviolet, physical prevention methods, ultrasound combined with the air purification systems, and a number of other methods. And the last point that I would like to draw your attention to is the fact that the space research spaceflight program and colonizing other planets has as its ultimate goal the understanding. We need to figure out how life appeared in the universe. Does it exist outside of Earth? Are there premises for it appearing on other planets? Paradoxically, but the development of cosmonautics can actually compromise this expensive and difficult program unless we envisage the possibilities of contamination of other planets with Earth microorganisms. And from the standpoint of an Earthling, there is an even more significant danger, that is, bringing back to Earth with the space vehicles of some other life forms from the outer space, provided they exist, or bringing Earth microorganisms which have been modified in an unknown and unpredictable ways under the conditions and in the atmosphere of other planets. Therefore, the planetary quarantine or planetary protection is extremely important. The first step to resolve this problem would be our understanding as to whether Earth microorganisms, which inevitably contaminate space hardware, be preserved for a long time over the period of time comparable to the duration of an interplanetary flight, such as the one to Mars, under the conditions of open space. We already know the answer to that question, and the answer is yes. A biorisk, an experiment that we performed recently on the outside of the Russian segment, on the outer shell of the ISS, had taken 18 months, and it confirmed that microorganisms, the spores of microfungi, can retain their ability, their life ability for that period of time. And interplanetary flights will be under different conditions, as the previous speaker mentioned. However, I don't think they will be limiting for the microorganisms, because only they can withstand radiation exposure up to 1 million rad, and they can actually live in the cores of nuclear reactors. So the planetary quarantine issues are extremely important and need to be resolved. I'm afraid that I'm running out of time, and just one more point. In the year 2009, we are planning to launch a vehicle to Phobos, and of course it's an unmanned vehicle that's going to fly to a satellite of Mars, and we are planning to put biological objects on board of that vehicle, microorganisms first and foremost. However, they're not the only ones that can survive in the unfavorable conditions. There are some others. So we are planning to put on that vehicle some biological samples, which will be later returned to Earth, together with the soil samples to be taken from Phobos. Thank you very much. Thank you very much, and I believe it's a very important problem that you raised, not only from the standpoint of ensuring the safety on the currently operating stations, but also in the sense of future interplanetary flights. Just imagine that we can discover on Mars those microorganisms that have already been brought there from Earth, and we will be saying there is life on Mars. Or if we bring down to Earth transformed, modified microorganisms which can represent danger not only for crew members but also for the population of the Earth. I would like in particular to suggest to our participants of the conference to voice their opinions pertaining to some off-nominal, unusual contingency situations when we establish standards for the habitation environment. We expect that they will be utilized, that the environment will be used nominally. However, as was already mentioned, we have gone through the cases such as fire on the station, a thermal destruction of some materials, and the depressurization of some parts of the stations, oxygen generation system failure, and CO2 removal system failures, and a number of other problems. So under the circumstances when it is possible that chemicals may be modified and some toxic elements may appear on board the station. So with respect to that, with respect to countering the off-nominal situations, I would like to hear your opinions. Let's start with the astronaut.
With off-nominal situations, there have been many, and we could go into various kinds. And I may have missed, did you ask me for a specific type of off-nominal? You guys were hearing that, just in general. There's the kind
I was asking
Bob
about
should.
your attitude.
There's the kind that'll take you out right away, and there's the kind that are kind of a slow evolving emergency where you can plan what you're going to do. Slow evolving emergency. I've been involved in most of those that you've talked about one way or another. Power failures on the space station. Nothing gets quite so quiet. And CO2 buildups, attitude control losses. I was trapped outside the airlock in the Russian suit when it wouldn't repressurize and never did, and we had to go make a backup emergency ingress. The training does get you through that. Anatoly and I, Pavel was up there when we had to do that, and we never were able to repress that airlock, and we had to disconnect from umbilicals, and you may have 10 or 15 minutes at that point before you'll overheat to the point of unsurvivable. And that you fall back on the training. When I look back, I kind of shudder at that situation. How did I ever get to that? But at the time, it seems like a normal course of business. Backup systems are critical, I guess, is one of the key points, or I wouldn't be here talking to you. Backup systems, when we lost attitude control, we spent several nights operating the Soyuz to bring it back, to get power back, to regain attitude control. But it relied upon a secondary spacecraft. I think lessons we learn over and over again with the space suits, the U.S. suits have gone down to the pumps that Mr. Gerstenmaier brought up. We relied on the Russian EVA suits, the Orlans, to do critical EVAs during that time to sustain the ISS. So there is a place for independent systems that aren't built. I always get a little nervous when I hear this one's built not to fail, or the life support system's built to never have microorganisms accumulate, or the radiation protection will be so good that we don't need to reconstitute our hematopoietic system if it goes out. There are themes there. Does that capture part of what you were after?
It is extremely important, the information that you're saying, because the medical community needs, in its preparation for major projects, have algorithms of responding to any situation, getting out of any situation, so that first and foremost they would protect life and health of the crew members. And with respect to EVA, that is a special situation, because a spacesuit is like a miniature vehicle that has its own life support system, and we did run through some problems periodically in that respect. Marcello, your turn, please.
In terms of radiation of nominal situations, during the Skylab mission, during the Mir and Salyut and International Space Station, there has been several solar particle events. And again, we are lucky because they were under the magnetic field. But they're common, they are standards, and Mario can talk about operational procedures and to deal with that. But again, when we go beyond that, on the moon surface, doing an EVA 10 kilometers away, if a solar particle event occurs, it's a different scenario. And of course, if you're in transit to Mars after 6 months of exposure to galactic cosmic rays, and also you have a solar particle event, well, what are the reasons those conditions? They are completely different. But in terms of radiation, yes, we have some of nominal, if we can characterize like of nominal solar particle events during International Space Station, and we have some astronauts that can tell us about that too.
Well, there's members of.
Thank you, Nigel. Your turn, please.
There are members of the audience who are much better qualified than I am about being on the receiving end of off-nominal events, but I'd like to go to one which is, we've picked on our Russian colleagues for the Mir fire, but let's look at our own problems. The MEDOX regeneration event, which, for those of you who don't know, the MEDOX system is for the EMU removes carbon dioxide. once it had been used and left in the system, it wasn't realized that the air was continuously being circulated through the canister. When it came time to regenerate the medocs, they're placed in an oven and then air is blown through them, and unfortunately about a year and a half's worth of contaminants which had built up on the medocs canister were dumped immediately back into the cabin, which sent the crew scurrying into the Russian segment for a day. So again, these are all things that we could not have predicted were going to happen. So I think that's one important one to notice. I'd like to go back to the acoustics question, and I'm not sure which panel member brought that up, but there are medical aspects to the acoustics issues, which again some of the folks in this audience would be much better qualified to talk about. But the other aspect of a high acoustic environment is the fact that the communications are difficult. Some of our crew members are wearing hearing protection for 16 hours a day. So when you have to talk to someone who's 6 feet away from you and they have to keep taking out earplugs to talk to you, that's not a good situation. So I think in terms of the future, we have to be very careful that the requirements that we set for acoustic environment for future spacecraft are met before you fly. We didn't do that on station, but we've got to do it certainly for a 3-year round-trip mission to Mars. You can't have a crew exposed to that level of acoustics for that length of time and expect them to be able to be first of all, medically fit and also psychologically fit after that amount of time. So those are the two I would choose.
Thank you very much, Mario.
I think I would agree with that. Having 3 teenage daughters that make a whole lot of noise, that sounds a whole lot worse to me than the radiation problem. Marcelo talked about solar particle events, and I guess I'd like to give a perspective on a specific solar particle event. Not that it was a bad solar particle event, but one that kind of changed some of my thinking as we go forward towards exploration. Generally, we look at planning EVAs around the passes that involve high areas of radiation exposure. So we avoid, the South Atlantic anomaly, and we avoid the high latitude passes if we can during the phasing for an EVA. We make those recommendations to the program in order to keep our crew members' exposures low. So during STS-116, at the very bottom of solar minimum, when all probabilities would say that a solar particle event would not occur, a couple of solar particle events occurred each time we decided as an agency to go EVA. We still made those decisions to go EVA because the resultant radiation exposure was not considered to be excessive or to be particularly a concern, and that the objectives for the mission that we needed to accomplish outweighed that increase of radiation concern, or the increase of radiation exposure. So that was kind of a shift in my thinking as a traditional radiation safety professional, and say that one of our goals or one of our planning for these missions that I'm talking about, we're going to plan with what we know now, we're also going to have to be able to plan to kind of be EVA enabling. If the plans on a lunar base is to explore the moon, we're going to have to go EVA all of the time, and solar particle events are going to occur, and they're going to be just part of the mission. So that was kind of a shifting in my thinking, and not quite there yet, and I'm not sure all those procedures are there yet, but it was just kind of a new approach to it and what risk would be allowed to be incurred.
I guess.
Thank you very much.
I just comment. I think what you imply there are good solar particle events and bad solar particle events, right?
It's a matter of magnitude, yes.
Okay, thank you, Natalia. Please. I would like to add a few words. It seems to me that one of the most important elements of responding and stopping the off-nominal situations from the standpoint of eliminating the risk is improvement at somewhat new level is the microbiological monitoring and control system. Particularly for interplanetary flights, we need to develop new express methods that would be adequate to the task at hand, that would be available even for non-specialists, even for cosmonauts who are not microbiologists, but to do it so that they could use those methods and answer the questions in a timely manner as to what's happening to their microflora of their environment, or water, air, and surfaces. And so I think that this point could be extremely helpful under the situations of those off-nominals. Thank you very much. And if we're talking about off-nominal and emergency situations, the difference is quite dramatic, because off-nominal situations were logged at Mir station, and there were several times, for sure, 4 or 5 times, and that was done, that had to do with the changes of radiation environment and the trajectory of the space vehicle. And so the radiation exposure risk also changed. The changes were small, since the trajectory of the orbital stations, both Mir and the ISS, is protected by the magnetic field of the Earth. And so in radiation safety sense, it's favorable. And I wouldn't say safe, because, any additional dose increases the overall hazard. And so the second thing is that along the trajectory of the orbital station, there is a category of a normal situation. However, it exceeds the normal background conditions on the ground at 5,000 times. So I will say on board there is, say, 50 rem annual allowable dose, and for the population on the ground it's 0.1 millirem, so it's 5,000 times difference. So there is a danger. However, the space is set up that way that in order to, when we're trying to bring down the radiation exposure on board of the station, we can't even bring it to the levels acceptable for the professional nuclear plant workers, since the protection will be so massive that we would not be able to launch that vehicle. So the compromise between the usability and risk is that we accept the risk level that is higher than that acceptable for the professions on the ground, but it's not so high as to threaten death of a cosmonaut. But the situation for the long duration and long distance spaceflight will be exacerbated, since we will not have the protective effect of the magnetic field. And when in orbit we had seen a somewhat small increase of the radiation exposure because of solar particle events. At the interplanetary leg of the flight, that exposure levels will be very considerably higher by several orders of magnitude, and so we would need to envisage some protection. There is another problem, though, and that is risks that occur due to a number of unfavorable factors. And as a general rule, when you establish limits for some factors, for this or that factor, they are set on the basis of the experience accumulated on the ground, on the basis of the experiments, and they very rarely take into account that there may be some other factors resulting in additional risk. And so when we take a look at Dr. Savin's, our distinguished American colleague's presentation, there are 52 risk factors, and each of them contributes to the increase of the possibility of lethal outcome or further unfavorable developments. Just a couple more words. If we just add up those risks as the probability theory requires, then we will end up with a completely unacceptable levels, and we need to take that into account. when we put in limits on certain risks, we need to remember that there are other hazard-inducing factors, and the total hazard can be catastrophic. Sorry for my lengthy statement, but it's very true, very important. That is very true, and it is in fact very important. Thank you very much. We have a few minutes. We have some time for questions and answers. Does anybody have any questions in the audience, please? And please use a microphone when you ask your questions. Do you have any questions? No? Everything is clear? Well, if we don't have any questions, then in closing, I would like to say that the environment is a multi-factor element that requires setting certain limits, constant monitoring, and it's very important that those norms and standards, particularly pertaining to radiation safety, require new approaches for interplanetary flights as compared to the low Earth orbit. Go ahead. Do you have a microphone?
None of you have mentioned lunar dust as an environmental risk. Could some of you comment on that?
We're real worried about it in the EVA world because we want to go out EVA very fast, and we don't. The concept is dock the suit and then open the back through a rear entry type system and come out. There's going to be an interface. And you have the contamination issues that were talked about, of course, but then there's also the interfering with the systems, and cleaning it up. So we need kind of a porch, and the whole EVA system has to be designed to avoid that, including the rover, pressurized rover system.
And Dave, to add to that, there's a plethora of folks out there right now that are involved in looking at the toxicological aspects of dust exposure. Going back and looking at the Apollo experience, not only the physical issues of zippers not zipping, but also the exposure to the human. And it's going to be long duration. I mean, Apollo operations were days. If we're out there now for weeks or months, then obviously we've got to do a lot more research in that area.
Yes, I don't mean to add fuel to the fire, but since Dave Wolf brought up the issue of stem cells, since skeletal muscle, which is the largest organ system in the body, relies upon its own stem cell system in order to allow growth to occur, in order for the fibers to enlarge, we also know that if you irradiate with low gray stimuli, that you can knock out stem cell proliferation and differentiation into the myofiber and thus prevent muscle hypertrophy. So the question is, if we are going to expose the skeletal muscle system to a dynamic program of exercise in the face of an atrophy stimuli that could be occurring, it behooves one to think about whether or not the homeostasis of the muscle in space with all this cosmic insult might be a problem. And I don't know if there is a need to factor that into the research mission.
Can I comment? Yeah, this just to make the situation a little more complicated, and I will address that issue. We'll go to space, and in particular in a long-term space flight, in particular Mars mission, I suppose. A big question for many, many years was the synergism between, for example, microgravity and radiation. And other factors, too. We are talking about microbiology, we are talking about dust and other factors. And up to this point, we don't have an integrative view in how all these factors will interact with each other. And we established limits or we established protocols and experiments based on radiation alone effects. This is very difficult to integrate multi-factor analysis in this problem. But we need to be aware that multiple factors maybe we will produce a different response in the radiation damage or repair capability. In terms of stem cells, based on experiments in the United States and in other countries using particle accelerators, we know that stem cells and progenitors are all very sensitive to radiation and very sensitive to cosmic rays. What is the implication for human physiology? Still, we don't know exactly. But one experiment that demonstrates the potential implication of this is the radiation can deplete some stem cells and hippocampal, the brain area. In animal studies, that depletion can have some functional implications in animal models. And that potentially give us some signal something is going on there. We know that stem cells are more sensitive to this particle radiation. We don't know exactly what is the physiological or operational significance for that, but this is a big question, and I think it needs to be addressed. And actually, NASA program is addressing those issues, and NSBRI in a limited fashion also too. And muscle is an emerging area that I think that we will pose new questions and need to be addressed on that regard too.
Interesting point.
Thank you very much. Thank you very much for participating in this panel. And we have run out of time, even though the topics were just briefly outlined. They require serious work, serious subsequent work. Thank you very much. Thank you all.
Apologize for being late. It's great you were able to come. Thank you for joining us. It's really a great pleasure.
Well, let's go ahead and proceed with the next panel presentation. And while the panelists are changing places, the next panel is headed by, the next panel is focused on the human effects of long-duration spaceflight and the human factors, events in flight, evidence-based. The panel moderator is Dr. Miraban Whitmore, who's the manager of the Usability Testing and Analysis Facility at the Johnson Space Center and the principal investigator for a project to develop a computer-based guide for handling medical emergencies in space. Dr. Whitmore.
Actually, I'll sit and talk. I always get very passionate, so if I start talking, you have to calm me down. I've been working human factors over 15 years now at NASA as a contractor first and later on as a civil servant. But as I was thinking about for this audience, first of all, I'm very honored to be here and getting ready and thinking about what will be the critical questions we can ask and how it relates to the medical area. That made me think about when I was 8 years old, I was actually in Turkey sitting in a small room watching a black and white TV and watching the first landing on the moon. And at the time, it was a dream that will never happen that I can witness or even be here. And then I remember myself being in graduate school, sitting in an auditorium and listening to, actually, I still get pretty emotional, watching one of our professors giving a presentation about simulating how to land on the moon for Apollo, and talking about, how exciting it was that they didn't know what they were designing for, and yet they had to train the astronauts for that unknown environment. And now, this year, actually, I started working for Crew Exploration Vehicle, working as the human engineering system manager that will help us, hopefully, to go back to moon. And it's just unbelievable that I'm actually kind of living a dream, and it's actually real. So having said that, our area is a little bit different than medical, but I think there are a lot of synergies. As human factors, I will kind of briefly mention what we say, and actually one of the definitions that I like the most from Alphonse Japanis is it's really the study, discovery, and application of information about humans, their capabilities, limitations, and other characteristics that will apply to implement it to design of tools, hardware, systems, tasks, you name it. And so anything, even this room, a lot goes to designing that chair you're sitting in. And how many times you sit at meetings and complain about the chairs, or complain about when you use any kind of new device, that which button to push to turn it on. And we have examples on ISS. I think one of the ones is the auditory terminal unit, push to talk, how challenging it is to the first time you see it. So, but anyway, that's really the user interfaces and what goes in it, and you're really combining the human into the system and designing it such that it's very easy to use, easy to maintain, and safe to use and efficient to use. And that's going to make everybody happy, and it will be, of course, add the productivity. So having said that, I will be actually introducing our panelists, and we'll ask them to briefly tell about their area of expertise to set the stage for your questions, so you're kind of familiar with their experience. Here to my right, we have Dr. David Dinges, and we have astronaut Mike Fink, and we have Dr. Vadim Gushin, and Dr. Jack Stutzer, and last but not least, we have Dr. Frank Carpenter. And if you can actually briefly talk about your area of expertise.
So I'm in the Human Factors Society. I'm a psychologist. I'm a professor in a medical school, and I study biology with mathematical models. And actually, all those portray my interests. My primary interest is in understanding when a human's going to make a mistake, predicting it in advance, and preventing it. And I don't mean necessarily a human with a pathological condition. I mean a healthy human. We often talk about the behavior human factors area as though it has no biology, when in fact the very biology that underlies pathology or depression or something, the brain's the organ of behavior. It's the same brain that's learning and operating and doing all sorts of other things. So I'm interested in the biological basis of it, particularly how technology can be used to identify human error before it occurs in what I call lethal or near catastrophic environments. And I'm talking about everything from B-1 bombers and spacecraft to hauling gases on the ground, to submarines, to any place a human goes, including a surgery room, to operate or to function.
I'm personally not an expert on anything, but my background is a flight test engineer in the United States Air Force. That got me a chance to understand and appreciate the human-machine interface for different kinds of aerospace vehicles, as well as for the getting ready for the International Space Station. I spent a lot of time working with the teams that were building the procedures and displays for the space station, both in the U.S. and in Russia. And that was a great training environment so that I could serve aboard the International Space Station for 6 months. We had a very amazing mission. And I'm getting a chance to go, looks like, fly again next year on expedition number 18.
Well, I think it's not so important who you are, but it's more important what you are doing. And from this point, we in IBMP we're doing the psychological support of the space crews and other kind of operators working under extreme environments. And later I'll try to explain what kind of problems we have in this area.
I have worked in the field of, I was trained to be an anthropologist, but I work in the field of human factors and ergonomics, and have been involved in space-related research since 1981, and presently have an experiment on the International Space Station, and have frequently been asked to explain the field of human factors to engineers. Earlier, Pavel Vinogradov talked about engineers as viewing the humans as just another system in the spacecraft, and so I try to relate to the engineers and the terms that they understand, and so I describe the human as an integral component of that system, and then in a few minutes perhaps I'll have a chance to describe what I say.
I'm a psychiatrist and a flight surgeon. I had the behavioral health and performance at JSC, at Johnson Space Center for NASA. As a behavioral health and performance person, my focus, or our focus as my team, is on performance. How does behavior affect spaceflight performance? And looking at spaceflight performance, we always approach it with four things in mind. First of all, the brain or the nervous system as an organ system, as a functioning organ system. Another second consideration is the psyche, the operational psychology support services and systems that we offer. Also, there's the physiological concerns, the neurophysiological concerns, and primarily in this environment, it's looking at sleep and circadian issues. And last and certainly not least is the human-to-systems interactions. And the human-to-systems interactions is probably my weak link, and nonetheless I'm on this panel. But the human-to-systems interactions are very important. I might add that I've had the fortune to work with 5 expedition crews while they're on orbit. So I've gotten feedback from crews on what their concerns and issues have been, and workload, the quality of workload, and the interfaces are always very significant to every mission. It was brought up earlier that it's difficult sometimes, if not impossible, for short-duration flyers. Dave Wolf mentioned this. For short-duration, no, it was Leroy Chow, I think, mentioned. Short-duration flyers cannot fully appreciate long-duration flight demands and impacts. I find that it's sometimes difficult for long-duration flyers to appreciate how much one mission changes from the next mission, because as the platform changes in complexity, as the systems get bigger and there's more maintenance to do, more timeline demands, the missions actually change. So focusing on performance is what we do. And in the human-to-systems arena, specifically early on in my time working here in this position, cognition kind of fell out as a very important interface between the health and medical side of what we do and the performance side of what we do. They really meet there. Is a person ready to perform a critical task at a critical time? That's one type of cognition that's very big in the human factors arena, but there's another cognition that cognitive test that we fly on orbit is used to monitor, and that's looking at the clinical medical cognition to make sure the nervous system is intact and people are operating optimally from a cognition and brain load perspective.
Thank you. Before we start over, I really would like to see that it's really interactive, that we expect your questions. The first introductory question I would like to ask is in your areas, for each of the panelists, what would you consider the top 3 challenges within the human factors field?
Well, I would say the first one is to convince people that training and motivation, while essential, are not going to be enough to prevent human error. And since human error is the root cause of 60 to 95% of everything that goes wrong in every industry studied, and there are whole books and studies on this, including commercial aviation, you cannot stop human error from victimizing you. Which means if you use only training and motivation, we have to basically be able to track behavior. I know that behavior is often thought of by many of you as a kind of psychological state. It's your consciousness. It isn't to someone like me. What I care about is what you do, not what you think. Okay, I want to know what are you going to do next, and how do I know what you're going to do? And that actually can be understood scientifically, and there are lots and lots of laboratories that understand it. And we can begin to get an idea of it, what's involved in limiting it, and by combining that with an understanding of the biology, of the temporal control of cognitive functions, etc., as well as environmental factors, human-machine interfaces, we begin to understand. So the first thing is understand that you can scientifically understand behavior. It's not nearly as idiosyncratic or arbitrary as many people think, and it can help improve your prediction and prevention of human error above training and motivation, in addition to those. The second thing is to recognize there are many ways in which humans become incapacitated, and they don't always know it. And in fact, this is a very serious problem in many systems. When things go wrong, they mistake their motivation to perform with their actual performance capability. This leads to a catastrophic outcome, and it's commonly seen. You see it throughout National Transportation Safety Board reports and other major incident reports that the Justice Department looks at, particularly in extremely expensive, highly lethal, incredibly dangerous systems when things go wrong. And then because of the commitment level of the operators, they're convinced that pure motivation and commitment will carry them through, and it often does, but not often enough. And the third thing is then focusing on the use of technology to help people understand how they're doing, to feed back to them, to improve the human-machine interface, not just from the standpoint of the human understanding what knob or button to push or what color the light is, but I mean machines that are intelligent, machines that can see you, machines that can understand your voice, process its frequency, read your face. And all of this is not science fiction anymore. Including machines that can diagnose you for depression or machines that can help you with a conflict resolution. All of this is feasible. And so the trick is, how do we get that kind of science developed to the point where it's worth deploying it? I like it, and this is my role as team leader of the NSBRI Neurobehavioral and Psychosocial team, because we're focusing on software, no upmass. Okay, in other words, all you have to have is a computer on board, and we can send up the things that we think we're going to need to help you. Now, we're still a ways from validating it, but we are getting ever closer. And the value of this is it doesn't remove any responsibility from the astronauts. Quite the contrary, it should improve autonomous operation. It's a machine helping them understand where they're at. Then they can decide when to take the countermeasure, how far off nominal they are. The inter-individual variability among people, even among extremely capable people, Scott, forgive me, but surgeons, pilots, astronauts, is quite large. And particularly not when they're normally functioning, but when they're under provocation. And those inter-individual variabilities in recent studies appear to be very trait-like. They look genetic. And in fact, and so biomarkers are a big deal here, identifying how to optimize the delivery of countermeasures and feedback from technology that interfaces, that reads you. Not sensors. I'm not a big fan of sensors. What we know from studies we've done for other federal agencies is people won't wear sensors. They'll take them off. No matter how much they say they'll wear them, they'll remove them. So we need to be able to do this with a physics that doesn't rely on a sensor touching you. So those would be my big three.
Thanks. Mike.
A happy crew is a productive crew. and most of the production, if you will, on board an International Space Station, for example, I'm talking like in the 90%, is not time critical. It's not something that where you have to be on top of your game with your reflexes at their peak. Those are landing the space shuttle. That's a time critical kind of thing. But aboard the International Space Station, most of the things are not that way. And I would posit to you all that going to Mars is also 95% of the time things aren't that time critical where you're landing an airplane or anything like that. So how do you what are the human factors for the day-to-day operations? That's really what can really help us, or also get the crews really annoyed. And again, if the crew gets annoyed, then we become less. We can go down the negative spiral. So, what are the things in human factors that can really help? And because we don't want to make mistakes, but for the life of us, we as human beings cannot seem to make things easy to use. Or we haven't really often thought of how we're going to use something. And here's an example. We have a new module going aboard the International Space Station, hopefully later this year. It's called Node 2 Harmony. And part of our job is to clean its filters. and because we don't want the microbiological growth, etc. So this is a simple task. You take a vacuum cleaner and put on the filter, but in order to access the filter, we have to open up somewhere between 8 and 12 bolts each time we want to clean it. So we haven't figured, the engineers have a really beautiful design, but it's not, the actual use of it is not really thought all the way through for human factors. So we spend our extra time, instead of doing some really valuable science, we're turning bolts, and that can be frustrating. So it all kind of goes together, not just human factors, but also the feeling of the crew. And again, a happy crew is a productive crew. So as we understand our tasks on board and write procedures and human interfaces such as displays or the actual physical panel interface, if we do it with actual real human beings in mind, not just the engineers design it to meet the specification, and actually poll the experienced and astronauts to come in and get them, or other representatives, we can actually make the interfaces easier to use. And we found that aboard the space station before the very first flight. Some of the computer interfaces were absolutely abysmal. We worked very hard and pushed hard, and now they are better. They're still not perfect, but they're a lot better. And I hope we start out that way for our next rounds of vehicles.
Okay, 3 main problems. The first one is maybe too much happiness and prejudice. Why I'm speaking about too much happiness here? Because we heard Dave Wolf recently, and he said they managed to cope with such an extreme situations as fire, with any other incidents at this station. So they're so good, they're so professional, they can cope with everything. They're also happy because they have very well developed psychological support system which works quite well. And if you look at the results from Nick Kenna's study on ESS and on MIR, you will see that actually there is no depression, almost no fatigue in flight, no problems except slight psychosocial problems, but very, very, very slight. So everything is working quite well. Why to speak about psychology? We're all mentioning it, but in such a light manner. Oh, everything is psychology, everything is going well, and could be well in the future. And when I think about that, for example, thinking about the Mars mission, it makes me worrying. Because, for example, psychological support now is based on communication system. And how we're doing support? We are arranging the communication sessions as you heard today, but what about communication if there is a delay? What about talks with family if there is a delay, which is increasing? What about communication sessions for PPCs, for private psychological conferences? If there is a delay, I need help, but it will come, maybe, after some time. Will it work for the Mars flight? I don't think that this kind of happiness is good for us now, and I don't think it's fruitful. Being happy, of course, is very comfortable, but as for me, a lot of countermeasures which I use now are good in principle, but are good for orbital flights only. And speaking about the autonomous flight and autonomous crew, I don't think that they will rely on us so much. And here comes the second problem, the problem of trust. Trust is a good thing if you have it, but the more I work, the less I feel that trust from the astronauts corps. I understand them quite well. They're right. They are dealing and coping with stress in such a nice manner without us. And why they need us in this case. And what we're doing actually, we're spying. We're trying to find negative effects
of space flights to convince our administration to give us more money. Yeah? I don't see any positive effect in this approach, because actually it makes a barrier between me and astronauts. Who am I? I'm a spy. At the same time, we heard here that they could cope with anything. But how much this coping experience is systematized? If we have a book describing the stress coping strategies of cosmonauts and astronauts? No, we don't. Are we analyzing this experience right now in the scientific manner? No, we don't. Do we know what are the positive effects of space flight from the point of view of group dynamics? We know that despite all that cultural differences, they create a cohesive crew and work together in a very, very effective manner. So how much do we know how they are doing this? And how much we can use this experience for the future? I don't see any steps made in this area. And I think that we have to change our viewpoint and strategy of research, not to look at the drawbacks of the flight. Are you nervous? Do you have fatigue? Do you have stress or depression? I think we must ask them, how do you cope? How do you create a cohesive crew? And we have to do something with this experience and to resolve the third problem, which is culture. It was the issue created by my colleagues. They say that we need good selection, motivation, and professionalism. 100% I agree on this. What we have in the astronaut corps, very highly motivated people, they keep motivation extremely long, for about 3 months, 6 months, 1 year. Look at the street. Are there people there who can keep motivation for 1 year? I don't think so. Are they professionals? Yes, they are. They are professionals of the top class. But let's have another look at this. What does it mean? That means that consciously or subconsciously, they reject any idea they could have a problem. So that means they do not have the feedback if the problem is coming. And if it will come, it will be too late. This is one issue. Second issue, we heard from one of the previous panels that it could be better to send an engineer with some medical skills. And if you ask engineers, they will say, oh, of course, medicine is so easy. Let them try our engineering. And if you ask medical people, they give the same answer. Oh, no, this engineering is so simple. This is the cultural barrier, but this is not the national culture, but this is professional culture, which is the basis for a lot of prejudices, lack of trust within the professional groups, between the professional groups. We do not trust them, they are mission control. We do not trust them because they are medical people. We do not trust psychologists. So imagine the international group flying to Mars. Who will be the medical doctor? American? Russian? Engineer? That will be the basis for a lot of prejudices, I believe, inside the crew. But we are not analyzing this situation as a problem right now. And speaking about visions, my visions are very bright if I'm looking at the current status. But I'm very skeptical with my visions about the future, very different missions.
Well. I agree with Vadim that it is as important to look at the successes of small groups living and working in isolation and confinement as it is to look at the disasters that have occurred. There is much to be learned and much to learn to avoid as well. Returning to the three most salient human factors issues, number one is interpersonal relations, and that includes communications within the crew as well as communications with mission control. Number two is what Colonel Fink was talking about, and that is support of work, task support, having correct and properly vetted procedures, having equipment that was designed with human limitations in mind, as well as human capabilities. And habitability. Habitability is all those features, all those amenities that are intended to support sustained human performance. Things such as the table that Leroy talked about that had such an intangible value to the crew to be able to, you don't sit, but to whatever you do, hover around the table and have a meal together. Private sleep chambers, absolutely essential if you want to have sustained human performance for long durations. The historical record has shown many examples that support the notion that humans can endure almost anything. But if you really want to facilitate sustained performance, you have to do those extra things, provide those other features in order to support the humans. And maybe I'll get a chance to talk about that in a second.
Yeah, being at the end of the table, yeah, what they said. Mike, I really appreciated your comment about a busy crew is a happy crew. I think there's a lot to that statement. And then the following statement about a lot of happiness, there's some really busy crews. When I talk to people about what they plan, point one would be, my answer would be validated mission performance parameters, or what is a successful mission, and are we doing that with each mission? When I talk to people before they fly, I ask them what their personal goals are and what they personally want to get from their flight. And there's a variety of responses. But when I talk to them on their PPCs while they're on orbit, we look at, I will examine with them, how are you doing on those personal goals? And when they return, most of the time I find those goals are met. And like Dr. Gusham said, there's a lot of successes to celebrate. Despite many successes, and mostly successes, there are occasional crew members that will come back and say, I didn't quite get done what I wanted to do as far as X, Y, or Z. So a crew member will experience a little bit of frustration, and sometimes that frustration that they carry with them will be motivation to do better on their next flight or to have another opportunity to improve on what they didn't get accomplished on that flight. But I think if we look at validated performance measures, I think it'll go a long way to helping us choose the optimal crews for future flights. And echo what Dr. Stuster said about effective communications and teamwork and team cohesiveness. I think it's also important to have educated crew members regarding psychological skills and coping mechanisms. Getting an educated crew member, I think, is the approach. I've heard a number of people to say today that there needs to be a physician on the flight. I want to have a physician with me. I kind of doubt a psychiatrist and psychologist will be high on that list to go with us. And having said that, I think it behooves us to pay attention to training the crew members, particularly the commanders, as well as all of the crew, on coping mechanism, coping skills, and getting them as educated as possible on those approaches and that awareness as well. Thanks.
Thank you. And I would like to open up for questions. Yes, Helen.
Do I need a microphone?
Yes. Microphone, please.
Well, the question.
Do you have a microphone, please?
Thank you very much. The question has to do with the fact you've talked about human factors. You've talked about. Oops. Doesn't work. The question is, you've talked about human factors. You've talked about psychological support and communications, as well as circadian rhythms. And my question is that a crew to Mars, or even maybe on a moon station, will have a gender mix as well as international and cultural differences. And I was wondering if you would address this, the gender, and I was thinking about is biology really the answer? then is the biology the same between men and women and between different cultures dealing with the differences in gender?
Oh boy. Gee, I'll be the goat here. Right. If I wanted to design plan a mission with optimizing the probability for success, I would select a homogeneous crew. 6 Norwegian males, middle-aged, with some seafaring experience would be perfect.
That worked for the South Pole, right?
I agree, Jack. I think that's right. I mean, the fewer differences you have there are certain things that happen in an isolated and confined society that, unless you've experienced that in that kind of an environment, it's completely alien. For example, trivial issues are exaggerated way beyond proportion. People will blow up over some little issue among the crew or with their outside control source, whether it's from Antarctica or from an island in the South Indian Ocean to La Réunion, or from a center to headquarters. Any little thing gets blown up out of proportion. It is just a phenomenon that occurs, and the people will, an hour or two later, wonder, "Geez, why did I do that? Oh, why was I so upset about it?" And there are several others. Communications problems are always going to be there between headquarters and the remote duty crew. Imagine when poor Ames Research Center doesn't get the word on time from headquarters, and they interpret that as evidence that they don't care for us anymore. Same thing for all. It is small companies, large companies. It's a structural thing that happens, in addition to the phenomena that are just characteristic of isolation and confinement. It's not going to happen that we're going to have homogeneous crews. And so during the training period, the ideal circumstance would be to enculturate all the different members, genders and cultures represented, enculturate them into a expedition culture. It's very important to establish a spirit of the expedition and for all members to share common goals and a common understanding of what the purpose of their endeavor is. All those other differences, ideally, will be subordinated to the crew culture and the spirit of this expedition. All of the successful expeditions that I've studied had a very well-defined spirit of the expedition. Usually, the ones that failed did not. So that's my answer to that issue. May I just say one other thing, and that is a lot was said at lunchtime, especially at Mr. Gerstenmaier's presentation, concerning the methods by which reliability is ensured. Engineers use 4 methods essentially to ensure the reliability of any system. They overbuild it, that is, the wall is designed to withhold twice the pressure that it's actually going to have to hold back, or the valve 50% more than the pressure that it would actually have to hold. Systems are designed to be maintained so that when they malfunction, you have the spare parts and whatever to fix it. And in some cases, redundancy is built into the system. That is, you have online spares or a backup. What are the implications? There are four methods. Those are the 3 principal methods. And what are the implications of that from the human factors perspective? As I mentioned earlier, although the historical record shows that humans can endure austere conditions, the most austere conditions most of the time when necessary, it is important to overbuild the system to support human performance. That is, provide those amenities to the extent possible that are intended to support human performance. A place to retreat from the close proximity of your comrades once in a while, a private quarters. On station, it's large enough now where crew members can get away and be by themselves and kind of decompress. What people don't understand is close and constant interpersonal relations is very stressful. It's very stimulating, And if you don't have an opportunity to regain the psychological homeostasis, that is, get away from the stress, you can't go for a drive, it becomes cumulative and can be can threaten the health.
Jack,
yes.
Forgive me for interrupting. I think regardless, I think this area has to prepare for any combination of crew. It's not going to be selected based on what we say, although most of us would like to have input into that. But in the end, we have to be prepared to have whatever human factors, behavioral health technologies on board or available from the ground, or psychological support or understanding of team dynamics, while the crew is preparing and training together to idiosyncratically adjust to them and bring the full armamentarium of skills and countermeasures we have to help that crew, whoever selected, operate. So our job is actually to be flexible, not to assume that it's going to be this combination or that combination and to know for a fact that's going to be the case. We have to be flexible. We have to be able to deal with any combination of people from any culture, both genders, and varying ages.
And adding on to what Christian Otto had said earlier, taking that diverse group and putting them in an analog environment for an extended period of time, because to get an appreciation for time, a winter over, if you get that diverse group, put them in a place like Antarctica for a year, where they really experience firsthand what it's about going for the long run. That's a profound training environment, and experiences like that would be good to build on.
Yeah, a lot of expeditions that didn't work in the past, they weren't given the tools, and some of the tools weren't even there to make them work. We talked about engineers pretending to be doctors, but the astronaut as a psychologist or a psychiatrist is a really good idea. If we're given enough understanding and training of how to deal with others around us and understand how human beings react, then we can understand how to be a good leader when it's time to be a leader, and when it's a good time just to follow. And those by having a constantly switching or adapting system, tried and tested in an analog such as under the sea or in Antarctica, is going to really help us go. And then it doesn't really matter if we're the engineer or the doctor, whatever these roles that Hollywood teaches us to play, because we're not really just monochromatic, or the girl or anything. It'll all come together because we have the tools and understanding, and we get to try it out. And if we can't if it doesn't work over a year in the Antarctic, then it's not going to work on the way to Mars, for example.
I know it was first, and then we'll come to you.
Well, it's no secret that humans make mistakes, often random mistakes. And the art of human factors is making the human-machine interface robust so that it deals with mistakes. So every time Windows asks us, "Are you sure you want to save that document?" Or are you and so on, and they think, "Oh yeah, they got me. They're right." Now, most of us in this room have heard about the space stupids, and yet the psychological examinations conducted in space that I'm familiar with, which are short-term memory, reaction time, and so forth, don't show very much degradation. I wonder if the panel could comment on the space stupids, without examples, and whether you feel that there need be extra precautions taken to make our human factors interfaces more robust, more cautious, if you will, in space than they might be for the same kinds of people in a ground environment.
Can I answer that? I can give a short answer, and then we'll let the real experts speak. But the neat thing about watching so many crews go to Station Mir and International Space Station is we see the variability of an individual. Some people are really susceptible to changes in their sleep pattern. Other people are oblivious, so they can sleep anytime. And the same thing, I think, with these so-called space stupids. Some crews swear by them, and other crews said, "What space stupids?" One of the programs that we used, computer programs to help us assess our cognitive abilities, I actually, for the whole time I was in space, was higher, so maybe I have the ground stupids. I don't... But it all depends on the individual and perhaps the situation, too. nonetheless, that's no excuse to say, well, some people will have these. Will need the best. The thing is around. Don't design around that. Just make a really decent human-machine interface. Kind of like Apple's making a lot of money because the computer company and the iPod company because they make really good human interfaces. And we need to do those kind of smart, easy to understand, so we don't need so much training and so many things. Those kind of interfaces are the best, and it doesn't matter if we're stupid or not.
Larry, it is true that the primary approach used in the United States is to engineer the human out of the system to the point where mistakes drop. That's why we have wider highway lanes and Jersey barriers and shoulder rumble strips and passive and active restraints so a more impaired driver can operate. But in highly lethal systems with a few people where a single human error can lead to catastrophic outcome, that isn't going to completely work, trying to take the humans out. And we know there's no reason not to use potent biological models of cognitive function and human error, whether it's sensory perceptual or decision making, in trying to understand and predict error in these environments. Neuroscience is incredibly sophisticated now, and we're getting better and better at using very small measures to detect. We have a system right now for Homeland Security that can tell us with a very high degree of certainty the likelihood that someone searching for a threat in an X-ray image is going to miss it. And without touching them or them knowing anything about what's looking at them, just watching them. And so I think we underestimate the potency of what can be done here, and we sell ourselves short not to use the state-of-the-art science in this area. I don't know what these words, space stupids, are. I don't even like to use words like that. And the amount of data we have from space on cognitive functioning is staggeringly little. And many of the tests that go up are not built for multiple measurement over time. They're affected by aptitude, which isn't as big a problem among astronauts because they're all very bright, but especially by learning. People keep getting better over time, so even if they're incapacitated, the score's still going up. What we need to do is take the best measures developed in neurobehavioral science on the ground, no matter how simple they are, and that are not affected by aptitude and not affected by learning, and then show that those measures track when astronauts go without sleep or get impaired, and where they track under the ocean, on the land, and in space. And that's the approach. What we haven't done is really back up and say, what do we know about behavior and the brain and functioning and predicting it and understanding it and measuring it, and take that forward now into the space program. Because that system is heavily loaded with motivation and training as the primary model. And that's okay. That just isn't going to get it done. Not completely, certainly not for Mars or long stay on the moon, in my opinion. Not from everything I know about Earth and all the errors that occur in all kinds of systems on Earth.
Thank you. Computational power is advancing by leaps and bounds.
Correct.
And an enormous amount of what we're talking about here is really vested back, as has been traditional in the space field, with computational capabilities that are maybe a generation old. If we're talking about missions 20, 30 years from now, we can expect computational capabilities, and in particular the modeling of many of the issues that are being talked about by the panel, to have made vast advances. What is being done today to make sure that our crews will have full advantage of the capabilities that computers will be providing in 20 years to give them psychological, psychiatric help, medical help, so they can be more autonomous?
There is work on this. NASA has funded a development of the astronauts' scheduling assistant, a mathematical model that's derived out of a lot of good mathematical work on how the circadian and sleep-wake dynamics control cognitive function and errors, and that's well along. And in fact, we just have a paper coming out applying Bayesian statistics to that to increasingly make it more accurate for a given individual. In addition to that, though, there's modeling underway at Harvard in a similar domain and looking at light entrainment effects And there's modeling on work rest scheduling, and there's computational modeling on human error. Now, this is stuff coming out of the Air Force, but we're using it and participating in it. But I couldn't agree more with you. I think that computational modeling, mathematical modeling, to help in software to help astronauts know what to do when or what to take when in an honest environment is very much the future, and it is a keystone in the prevention prediction area.
Let me give you an example from another area. In chess, now it's very popular to play with computers, and you know that even the world champion Kramnik could not win the match with a computer. He actually had no chances because the computer was calculating so fast and using the standard system of playing no way. Of course, computer is better. But another world champion, the previous world champion, Anatoly Karpov, is saying now that it's interesting that such group of chess players, grossmeisters, who are actively using computer, cannot play with the human opponent because they rely too much on the machine, on the prompts coming from it. And strengthening computer, you create the reflex that the decision will be made by somebody else. You are not ready to take responsibility and think actively. So again, we must not be too happy with ourselves and our successes in the nanotechnologies and all these things. If you want the perfect combination, it's still a combination of man-machine. Because it's so easy to switch machine off. And even if it's perfect, it will not work in this case. And even if this operator will trust this machine too much, he will lose all his advantages as a human being. So I don't think that we have to speak too much about the decrement of memory or attention in space flight. We better think about how to provide the professional skills necessary on Martian surface or lunar surface, how to create opportunities using computers to make the flight interesting from the point of view of acquisition of the new skills, so people can really do different professions as a result of the flight. For example, I am an engineer, but I'm interested in biology, and during the flight I have 3 years. I can study biology, have some other skills, and if, just in case, the mission lost the crew member, biologist, I could be his substitute. I think this is more productive than to think, oh, we'll create so wise machines, send them, and I will be just a pilot who will get the medal after the flight.
Well, that's not what we're working on, but
oh yeah, NASA's working on it.
The interface issue is the key issue, and this actually brings it back to the classic human factors area. We have learned over the years that no matter how accurately we can track or predict somebody's ability to attend or remember or respond, they won't use it if the interface doesn't make sense. And this goes to Mike's point very much to the heart. And I have to confess I was a skeptic in this area till we actually tried to deploy things operationally, not with astronauts, but I got a big lesson right away that no matter how much it made sense to us, if it didn't make sense to the user, it's not going to work. So there's a significant amount of work that has to be done to figure out in what ways do the astronauts want the data to be available to them, and what would they want to know about it to be able to decide themselves whether they want to use that information or not. How do we make it optimally helpful to them without them being dependent on it to the point that they can't do the job without it? It's more a matter of making it an aid. And I think that's going to be the real challenge, where the people like me have to work closely with human factors people and with the users to get these technologies really deployable in a useful way. That's where analog environments also come in, NEMO and that. We can start looking at some of the interfaces in those environments, see how astronauts like them.
think, were you going to ask something? I know you were raising your hand beforehand. But...
Oh, thank you.
Yeah.
I was interested in either small groups or medium-sized groups dynamics, and whether or not there's a preferred number that is even or odd, or number of people, and if there's any preferred leadership style that would be useful for such long missions.
Years ago, there was a sociologist who said it should be an odd number group so that when votes are conducted, that it's not a tie. And I would not want to go on an expedition where every decision was made by a democratic vote. It would be unwise to do that. You should have the number of crew members that you need, that your task analysis that's conducted systematically beforehand instructs you that you need, and no more than that. But it's not even or odd, and I've searched the literature looking for it. I'd sure like to know if anybody else found anything about that. The other method, by the way, that I didn't get to of ensuring reliability is redundancy. The space program did not invent triple redundancy as a method for survivability. Columbus never would have left Spain, nor would he have returned if he had departed with fewer than 3 hulls. And all of the talk today is about a spaceship. And I think that not only the systems on board need to be redundant, but that more than one ship be sent at a time. The Santa Maria went aground on Christmas Day, 1492, and broke up. Well, there you go.
It was a user interface issue, right?
They were drunk, and they left the watch to a cabin boy, and one of the captains had mutinied and gone looking for gold, and that left Columbus with his smallest ship. And had the other guy not come back miraculously and found that little island, they wouldn't have made it back to Spain. Redundancy is important. Redundancy is important in equipment reliability. It's also what we've been talking about in cross-training with humans as well, with the human crew. You have to have every skill that you possibly will need on that expedition in multiple by cross-training.
I think... Well, I don't think that there is an ideal amount of people. Anyhow, I think that there will be engineers who will dictate how many people will fly. And we can imagine whatever we want, but they say it will be 6 or 3 or 2, and nothing can be done about this. But if you look at the distribution of psychosocial roles, and if you look, for example, at sport, you will see that the optimum team is 7 plus minus 2. And this is in majority of the team sport. And that gives us some evidence on the one hand, but if you discuss the leadership style, I don't think it could be one style dominating through the whole mission. I think it depends on the situation, and this is quite clear that under extreme conditions, to arrange voting, elections, which will be politically correct, that's not the way out. And of course, when the situation is smooth, and you can really make a meeting around the table, which is so important, and have a cup of tea or something and discuss it in a democratic way, of course, it's the perfect thing. But for the easy questions or for philosophical questions, for the strategy, if you have time. So again, nothing ideal exists. And the ideal gender composition, I don't think it's the question we have to answer. If the politicians will say we need a woman in the crew, there will be a woman in the crew, and nobody will take care what we think about that. The question is, what is the evidence? The evidence is that could be crews where the presence of a woman improved the situation drastically, and the situations when the presence of women spoiled it drastically. So again, it's not our question. I think our question is to find a way of support of the crew which will fly, and to be ready to support it, and to be not only ready to monitor. That's what we're doing with thousands of methods
more and more sophisticated, but to find the ways of support. And in this case, there will be feedback from the crew. The crew will be more open, prone to give us sincere answers, what is going on, and maybe afterwards we'll know that there were some problems. Anyhow, what cosmonaut Vinogradov said, I like it very much, the idea of choice. I think the question of choice is most important for psychology. If they have the choice of various methods of support, choice of monitoring systems, they can try by themselves as an autonomous crew. And if they have a need to make a diagnosis, what is going on with me, they will have this opportunity in the flight to Mars or to the moon. And of course, we have to be prepared for this and provide them all these facilities, methods, and ideology. That will be our role, which is not very, very big one, but still not yet done.
I know there are a couple of more questions. I'll get one last question, but everybody is very anxious probably to take a break, and maybe you can continue with your questions during the break. So one last one.
He asked for, this gentleman asked for 15 minutes already.
Oh.
I wanted to ask about the use of psychotropic medications.
Well, Dr. Carpenter, I think, can talk about that in terms of what's actually happening in the space program, but it is an important area.
The psychotropics that are used today are sleep aids at times when sleep shifts are mandated by the mission requirements. To my knowledge, there have been no antidepressants, antipsychotics, any major tranquilizers used. They are available and probably should be available on any extended duration activity. It's nice to have that as an option. But as was addressed earlier, our lack of knowledge and lack of information on like Nick Candace mentioned it, the route of administration and the optimal medication to use in those settings, we're going to learn as we go. The evidence base is based on what we do the first time we use it.
We're developing an electronic database to support the flight docs around knowledge of medication. That is, that they can quickly look up to see at what dosage you get carryover effects for what kinds of things. And we think aids like that will help them make decisions in a way that's good for them, good for the astronaut. And because that's being handled, isn't it, Frank? Pretty much it's a doc-astronaut thing. Right?
Yes, it is. Time for one more?
Can we?
Okay,
one more. Last one.
Chuck Owen from MIT. The U.S. military certainly has made some progress by instituting human systems integration procedures. I'm thinking of the Manprint program and CPrint and so forth over the last 20 years. And those of you, I think you might get, coming from the Air Force, you've had some experience with what are allegedly human engineered systems. And I was remembering several years ago, Terry Allard was trying to push to get human system integration more deeply embedded in the NASA culture. Do you think that that's a solution? Are we behind in this area, and should we push for this?
I think I can actually answer that.
You should, yeah.
Actually, there is a big work on not only updating our old MSIS, which has been, some of you may be already familiar with it, NASA standards 3000. So it's actually expanding it, not only having the standards, but also having the handbook that accompanies it as providing guidelines, design considerations, and incorporating all that information, but also collaborating with the military to look at the human system integration. And there are actually, as we speak, this week, they went and had some meetings and come back. So I didn't even get the debrief yet, but there is current activities actually close to working with DoD on kind of how to approach, how best to utilize human engineering integration, human system integration, and also getting their lessons learned. We're also hearing a lot of the lessons learned aspect from their practical application perspective. It's always nice to have the documentation, but when it comes to actually how you're going to implement that, how you're going to use that, and do you really understand it, those kind of lessons learned, we're also capturing that. And we do have also Human Engineering, DoD Human Engineering Technical Advisory Group. They meet yearly, and that's something we've been actually working with them. DoD group, there's also FAA, and NASA is involved. So there is current work. I can't say we finished it, but that's definitely going on. Thank you for participating, and thank you for your attendance.